Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, my name is Jesse Masson. I'm a postdoctoral researcher working for Professor Mark Lundstrom here at Purdue. I'm going to give a bonus lecture at the end of week 2 here. And so during this last week, Professor Lundstrom has showed how we can compute the thermoelectric transport parameters of materials from their band structure. Now, commonly, people will use simplified analytical expressions for dispersions. However, it can be quite useful to know how to compute the TE coefficients from realistic full band dispersions. And that's really what this lecture is going to be about. And in particular, we're going to focus on the example of an important thermoelectric material, bismuth telluride. So let's begin. Okay, so first question is, why would we want to use full band dispersions of materials? If we have simplified expressions, why don't we just use those? So there's 2 real good reasons why you would want to do this. And the first is that you want to extract meaningful and reliable physical parameters. In our experience, we found that if you use a simplified dispersion, you can probably manage to replicate experimental data. However, the parameters that you fit, for example, mean free path, you'll find that those numbers will be very different if you go back and you use a full band dispersion. So this turns out to be quite important. And the second point is you'd like to predict the properties of new materials where little or no experimental data exists. Thermoelectrics is a very active research field, and there's many new materials being developed continuously. And there's not always a lot of data. It's quite limited sometimes. And so it's nice to be able to do these calculations from first principles theory and have that predictive power to provide an answer. Okay, so here we have an outline for the lecture. We're going to work through an example of how to extract the thermoelectric properties using full band dispersions. This will be for electrons and phonons. And we're going to focus on the case of bismuth telluride, like I mentioned earlier. Specifically, we're going to look at the 4 following points, 4 topics. The first is we're going to review the thermoelectric equations, which you've seen extensively at this point after week 2. Then we're going to go ahead and look at how we compute the number of modes or the distribution of modes using a full band dispersion. Next, we'll move on to calculate the thermoelectric properties, the electronic thermoelectric properties, and then we'll calculate the phonon thermoelectric properties, i.e. the lattice thermal conductivity. Okay, so let's begin with a review of the TE equations. So I think you've seen this already many times. I'll just go quickly through this slide. Basically, thermoelectric principle shows that heat flow and current flow are coupled. So if you look here at the electric field and the heat current, you'll find that they both depend on the electrical current, which is this J sub x, and the gradient of the temperature across the material as well. And what relates all these quantities are the thermoelectric parameters, such as the resistivity, the Seebeck coefficient, the Peltier coefficient, and the thermal conductivities, the electronic part and the lattice part. So what we want to do is calculate these coefficients. And you've seen this already. This is the equations that we use to do this. So I won't go through this, but what I will highlight is that the central quantity that you need to calculate to do these calculations, to do the thermoelectric calculations, is the differential conductivities. So either both the electronic differential conductivity and the differential lattice thermal conductivity. So we're going to focus on these here. So typically, the Boltzmann approach is used for thermoelectric calculations. And we can write both of those differential conductivities here in this way. Essentially, we know everything, and except for 2 quantities, which are the so-called transport distributions for electrons and for phonon, which we need to calculate, and those are related to dispersion and scattering effects. Okay, so here, generally, we'll write the transport distribution in this manner, which will depend on things like velocity of the states, the scattering time, and here you see you have a summation over all the k points in the Brouin zone, and this also includes a delta function. So actually, at first glance, calculating this quantity might seem very tedious, but it turns out that if you use the Landauer approach, you can relate these two quantities are actually the same, and you can rewrite things a little bit more simply. So the transport distribution in the Landauer picture has a very clear physical interpretation. It's the product of the number of modes, or the distribution of modes, really, which is just the number of conducting channels per cross-sectional area. And this is actually only depends on dispersion. Okay, so the scattering physics don't come in at that point. And also, what I hope to show here is that it's quite easy to extract. You can calculate this without too much effort. And the second part is the mean free path for backscattering. And this basically corresponds to the average length traveled by a carrier, either an electron or a phonon, before being scattered into a backward moving state. So this actually depends a little bit more on sensitivity on scattering. Actually depends very much on scattering. And it also depends on the dispersion model used. Okay, so we did a quick review here of the TE equations. Now let's move on and show how we calculate the modes. Okay, so this is a general definition that we have. So if we have a 3D solid or a bulk solid, the number of modes is going to be, let's say the number of modes per cross-sectional area here, actually. So we'll have units of number of modes per meter squared is given by this expression here. So A is the cross-sectional area, and here you have a summation over k points here, perpendicular. I have a little perpendicular sign. So this is a sum over k points, but in the plane perpendicular to transport. So for a 3D solid, you're actually only doing a 2D summation. And often this is translated into an integration. Okay, so this n sub plus, this indicates that we're going to have a summation over all the bands as well, or branches in the case of phonons. And the plus indicates that we only count the positive velocity states, forward moving states. And then this theta here is really just a Heaviside function, and this makes it so that when we calculate modes, what we're doing is we look to see if a band has a state at energy E. If it does, we assign one mode. Okay, so the number of modes is easy to calculate, as I'll show soon in the next couple of slides. And we use this so-called band counting approach, which turns out to be a very efficient way of calculating the distribution of modes. Okay, so next we're going to move on. We're going to demonstrate this approach with two simple examples. We'll do a 1D case and a 2D case. Okay, so this is a 1D example. Now, the expression for modes looks like this. So we have transport along X, and we have no periodicity along Y and Z. Okay, so this means that we have a wire. Now, in general, the units are going to be meters to the power of minus D plus 1, where D is the dimensionality. And so in this case, D will be 1, so we have minus 1 plus 1. So M to power 0. So it's really just we're counting number of modes. Okay, so also, since we have no periodicity, we've gotten rid of the sum in K space perpendicular to transport, since there is no K space. Okay. So let's apply this formula for some given example shown here. So here we plot in red some dispersion, and we see that we have some bandwidth that goes from E1 to E2 here. Okay. So the way we calculate modes is we ask ourselves, okay, we pick any energy E prime. We ask ourselves, are there any states at that energy with forward moving states, so positive velocities? So in this case, you see you have 1 point here. Whereas in this case, it's backward moving, so we wouldn't count it. So what we do is we change the energy, and we map out the modes. So here we have modes as a function of energy, and we see that we have 0 modes up to E1. Then we count 1 mode during this whole bandwidth, so you have positive states. And then the modes go back to 0. And so one important point is that in 1D, the number of modes is just an integer. Okay. And if you want some more details on how this is done, also where this comes from, you can look at this reference here. So next we're going to move on to something a little bit more complicated. We're going to look at the example for a 2D case. Okay, so here, this is the expression for a number of modes in 2D. And in this case, we have transport along X, we have periodicity along Y, okay, and we don't have periodicity along Z. So in this case, the units, when we put in dimensionality 2, we get per meter, which means per width. So how many modes per width of a film that we'd be considering here? Okay. So in this case, we're going to consider a parabolic band, 2D. This shows the dispersion as a function of kx along the transport direction in ky, which is now perpendicular to the transport direction. Now, here we have an integral over one of the reciprocal space vectors, so ky. Kz isn't here for this integral. Okay, so the point is that when you do a 2D calculation, really what you're doing is kind of a sequence of 1D mode calculations that I showed on the previous slide. So if you were to take one ky here near the zone center or another ky here near the edge, you would do essentially the same procedure. You would plot E versus kx for each one of those ky values, figure out where the modes are, assign an integer. So if we do this for all ky values, we can make this plot here, this color plot, where you see energy as a function of ky. Everywhere in red, essentially you have one mode. Everywhere in blue, you have 0 modes. And really what this corresponds to is the integrand of this integral that we need to do. And then you can see the blue arrow corresponds to the zone center. You have basically one mode everywhere, which is what you would expect here. And then the red arrow would correspond to a ky value near the zone edge. So it's kind of like you would have to go to higher energy before you encounter a band. Okay. So like I mentioned, this is really the same as a 1D, but you do 1D example for each ky value. Now, if we want the total distribution of modes, then we have to integrate this as a function of ky. And if we integrate it, we find we get this function here as a versus energy. And because this is a parabolic band, we know the analytical result, and this is actually just something that goes as the square root of energy. Now, I'm going to stop here. I won't do a 3D example because it's essentially the same procedure, except you would now iterate over ky and kz and map out these types of plots in those cases also. So it's just a sequence of 1D cases that you do over the perpendicular k directions. Okay. All right. So you've also seen this before, but I just wanted to quickly reiterate the fact that the number of modes, or the distribution of modes, depends sensitively upon the dimensionality of your system. So in 1D, you'll have something that's a constant, whereas in 2D, you'll get something that goes as square root of energy. And in 3D, you'll get something that goes linearly with energy. Now, this is important to remember because it's going to come back later in this lecture. Another point also is that it scales, the proportionality constant here is the effective mass for isotropic parabolic band here. Now, you can derive a formula for an ellipsoidal band, and that will give us some density of modes effective mass, just like we have an expression for a density of states effective mass. Okay. All right, so now we're ready to compute the number of modes in the case of bismuth telluride. So this is for the electron dispersion. So here I showed the electron dispersion for bismuth telluride that I've computed using density functional theory. And one thing that comes out immediately is the fact that the band structure is very complicated, much more complicated than you're expected, that you see regularly with semiconductors like silicon. And so really this band structure cannot be well represented by a parabolic band, or it'd be very difficult to justify why you would expect that to work in this case. So we can go to the next step and compute the distribution of modes, which I show here. So this is modes versus energy. And what we find is that actually the modes are fairly smooth. They're not very spiky, and in fact you can almost roughly fit a straight line through the band edges here. Okay, so this is a rather surprising result given the fact that the EK itself is non-parabolic, but the modes actually are pretty smooth, and you can fit a straight line. And remember, a straight line for the modes means basically you're doing the parabolic band approximation. Okay, so we can extract some effective density of modes effective mass here. Okay. Now, I want to mention that you can do this. You can fit the modes and extract some density of modes effective mass, but it's not clear whether there's a clear advantage to doing this, because at this point you've already calculated the modes. A lot of the hard work's already done. Although I can see there's a slight advantage that once you have this effective mass, you can go back and get basically analytical or semi-analytical expressions for the thermoelectric coefficients. But once you're here, you might as well just keep moving forward since you already have the modes. Okay. So the next thing I wanted to mention is that KT, okay, KT is on the order of 25 millielectron volts at room temperature, and electron dispersions are maybe on the order of 10 electron volts. So there's a factor of 400 there. So really, what you're doing is you're probing essentially a small region. So for Fermi levels here, conduction will only occur a few kT around the Fermi level. So this is something to consider when you think about how transport occurs. As we'll see, phonons are actually quite different. And this also gives some validity. If you want to do a fit, actually all you need to do is fit some small region a couple of kT away, and you probably will do a not too bad a job. Okay, so next, let's look at the case of phonon dispersion with bismuth telluride. Here I show the band structure in K-space that I've computed from density functional theory. Again, the band structure is quite complicated. You have 5 atoms in the primitive cell of this material. Each atom is going to give you 3 branches. So you have in total 15 branches. 3 are always acoustic, and the rest are optical branches. And so looking at this, it's hard to justify how you could use a very simple dispersion model to represent these phonons, such as the Debye model, which would assume it's linear in K. Maybe that works for acoustic, or the Einstein model, which assumes that the optical modes are a constant. So we can compute the distribution of modes, and we get this. And so we see we get lots of features actually in this distribution of modes. And this relates to the specifics of the phonon dispersion. Now, actually at low energy, it turns out that you can represent these states fairly well with a Debye model. So Debye model, again, is linear in K for the energy here, and which translates into E squared. It goes as E squared for the distribution of modes. Now, there is a but here. Like I mentioned earlier, you see KT is 25 millielectron volts. But look at this band dispersion. This is less than 20 millielectron volts. So this is not like electrons. So if you wanted to represent phonons with a simple model, really all of this blue curve, essentially all the phonons here are going to be thermally active and contributing to transport. So it's difficult to justify how you could represent all of this essentially through a function that goes as E squared. So for accurate calculations, we find that actually you need to calculate the detailed structure of the modes here. Okay, so we're done with the number of modes. Now we're going to go ahead and compute the electronic thermoelectric properties. Okay, so here I show the expression for the differential electric conductivity. Now, like I mentioned earlier, this is the central quantity to calculate all the electronic thermoelectric properties. Now, we know basically everything here except one that needs to be determined, which is this mean free path for backscattering. So let's talk about how we extract this quantity. Okay, turns out with electrons, a nice feature is the fact that a constant mean free path turns out to be a reasonable approximation in many cases. And in fact, you can show that it's exact if you assume that you have parabolic bands and you're including electron-phonon scattering. The energy dependence drops out, actually, and it's exactly a constant. So I refer you to this reference here for details on that. And just to show how it works, we can go ahead and calibrate our mean free path to experimental data. So here on the right, I show Seebeck versus electrical conductivity. And all the markers here are experimental data points, and then the blue curve is theory. And what we find is by using a mean free path of 15 nanometers for the valence band and 21 nanometers for the conduction band, we can essentially reproduce all of the experimental data very nicely. So this gives some validity to this approach of a constant mean free path. But I also want to mention that you can calculate the mean free path directly from first principles, but this can be tedious at times and can be quite difficult. Okay, so now we have everything for the differential conductivity. We can go ahead and plot it. So here we have differential conductivity versus energy. Here 0 energy corresponds to the conduction band edge. So in blue, I show the numerical result. In red, I show this parabolic approximation. Remember, this is what we did when we fit the modes of bismuth telluride. We didn't fit the EK, we fit the modes, we extracted some effective mass, and this is the result you would get. So even though that fit looked pretty good, you have to be careful. There's some discrepancies here. So initially what we see is that the conductivity, differential conductivity, increases initially because the modes are increasing, but eventually drop down because of this Fermi window function, the occupation function, which is shown as a black curve here. That essentially suppresses everything. So that when you look at this, the Fermi level located at the conduction band edge, conduction, most of the conduction, the average conduction is always a few kT inwards in the conduction band, as you can see here. So now we have everything, and so we can compute all the electronic thermoelectric parameters, such as electrical conductivity. So it's just the integral of this quantity, which we show here as a function of Fermi level. Blue curve is the full result, the full numerical result, and the parabolic, again, we compare just to show what it looks like. So we see a result that we would expect. Essentially, we'd have a rapid decrease here once the Fermi level is located inside the band gap. You know, this is a log scale here that covers many orders of magnitude. And you can see that actually comparing these two curves, it doesn't work, perfectly. It does an okay job. So it's worth noting that you can do this, but you should be careful. And we can go ahead and compute the Seebeck coefficient, which I show here. You have this typical shape that you would expect where the Seebeck coefficient is positive when conduction is dominated by holes, and then switches over negative when conduction is dominated by electrons. Again, you see some features with the full calculation that you don't see in the parabolic approximation. We can calculate the thermal conductivity, the electronic thermal conductivity. And in this case, you see also the electronic thermal conductivity is very large when the Fermi level is located in the band. Well, there's many electrons contributing to current flow, and each of those electrons is carrying some energy with it. And I should mention that there's a little peak here. This is a common feature for the electronic thermal conductivity, but it only happens, you only see this feature when you're dealing with very small gap semiconductors. In principle, materials like silicon, this peak exists, but it's very small and decreases as the band gap increases. Okay, so next point, we're going to look at the lattice thermal conductivity. Okay, so just like before with electrons, we know essentially all of the quantities that allow us to determine the differential lattice thermal conductivity, except one, which is this mean free path for backscattering. Unfortunately, we can't make the same constant mean free path approximation we did with the electrons. That doesn't work very well for phonons, so we have to go ahead and compute things directly. So in this case, the mean free path for backscattering in general is given by 2 times this ratio of average velocities, which is defined in this paper here, if you're interested, times the scattering time here, tau. So if you have many scattering mechanisms, which is pretty common for phonons, you need to add them up in this Mathiasson type addition where you add up the inverse of each scattering time. Now, the typical scattering mechanisms for phonons, which typically occur, are in bulk materials, are umklapp scattering, like phonon-phonon scattering. You have boundary scattering, which really depends on things like the sample size. A phonon can't jump out of the material, so it has to scatter once it gets to an edge. And things like defect scattering are also important. So if you have impurities or alloys, phonons can scatter off of those. Now, if you're dealing with other material systems like nanowires, if there's some roughness at the surface, then that'll induce some extra scattering terms that you need to take into account also. Okay, you can calibrate this mean free path to experimental data, like we did with electrons, and we're going to do that on the next slide. Or again, you can go ahead and calculate the mean free path from first principles. This can be quite difficult and tedious, but it can be a useful approach as well. Okay, so let's calibrate the mean free path. Here, I show the lattice thermal conductivity versus temperature. Now, the blue markers correspond to experimental data points, and the dashed red line corresponds to theory. Now, in this case, I used a simplified expression for the scattering time or the scattering rate using Oop-clamp scattering. That turns out to be enough in this case. And we have two parameters, B and C. C I took from the literature, and I adjusted B to match the experimental data. And we get a very good fit over quite a wide temperature variation. And after this, we can extract an average, energy average mean free path for phonons on the order of 11 nanometers. Okay. I wanted to quickly mention that this shape for lattice thermal conductivity versus temperature is not very typical. More often, you'll see something like this, where you have an initial rise in lattice thermal conductivity, then a drop. So here, this is actually the case for silicon. And in this case, you really do need to take into account all these other scattering mechanisms to properly reproduce the experimental data. And in this case, you'll get an average mean free path of about 140 nanometers. So you can see there's quite a bit of variation from one material to another in terms of mean free path. Yeah. All right, here I just wanted to quickly mention also, if we plot the mean free path versus energy, you see that there's the mean free paths for phonons vary by orders of magnitude here. So this is like 10 microns, and this goes all the way down to about 1 nanometer. And so really, this is very different than in the case of electrons, where you could assume that the mean free path is just a constant. But you have to be careful and keep this in mind, because the average mean free path that you extract might be actually quite close to that of electrons. But you have to keep in mind that this can be, the energy resolved mean free path can be quite different. Okay, so let's combine the electronic and lattice thermoelectric properties to determine the TE performance metrics for this material. So first thing we'll look at is power factor, which is the Seebeck coefficient squared times electrical conductivity. So here I show this as a function of Fermi level position. So the blue line is the full numerical result, and we see that actually the power factor is maximum very close to the band edges, and in fact a little bit inside the bands. So the band edges correspond to these vertical lines here. And another point is that there's lots of features here from the full calculation that you see isn't captured from this parabolic approximation that, remember, we fit from the modes of the bismuth telluride. Okay. Now, if you look closely, you'll see for the valence band, the optimum Fermi level that to maximize the power factor is different in both cases. Now, this is important, because if you have an experimental collaborator that says, tell me where my Fermi level needs to be to maximize performance, or equivalently, tell me what doping concentration I should use, if you use this parabolic approximation, you'd be getting the wrong answer, actually. So it turns out to be quite important to do these calculations. Next, we look at the figure of merit, ZT. So ZT is directly related to the efficiency, the thermoelectric efficiency. So this is the power factor here times T divided by the sum of the electronic and the lattice thermal conductivities. Okay. Again, you see the ZT is strongly peaked quite near the conduction band and the valence band edge. And again, you'll see that in the valence band, the parabolic approximation really doesn't capture all the features, and the optimum Fermi level position is a little different, which is something you'd like to capture correctly. Okay, so this is just repeating that if you do this parabolic approximation, fitted from the modes, which seem to work well, in the end, you have to be careful. You might be missing many important features. Okay, so in summary, we find that full dispersion-based thermoelectric calculations for electrons and phonons are particularly useful for two reasons. The first is we want to get meaningful and accurate physical parameters. We'd also like to use this to study and predict the properties of novel material systems, where this type of approach combined with density functional theory can prove very useful. Okay, now, within the Landauer approach, which readily spans from ballistic to diffusive transport regimes, one needs two things. The first is the number of modes, which we've shown here is actually quite easy to calculate from any general dispersion using this band counting method. And the second quantity is this mean free path for backscattering, which we can calibrate to experiment using simple expressions for scattering parameters, which is easy, or we can calculate this directly from first principles, which turns out to be quite a bit more difficult. Realistic descriptions of TE materials are not always well represented by simple band dispersions, so it can be a valuable skill to know how to calculate and predict the TE properties of materials that have complex electronic states, which actually turns out to be many thermoelectric materials. If I think of lead telluride, bismuth telluride, these are cases where you see that its parabolic band has to be used with caution. Now I wanted to mention that we've developed a tool called LandTrap, which is available on nanoHUB at this URL. And this particular tool takes in some general electron or phonon dispersion and then computes the modes and also all the thermoelectric properties from that. And it also considers things like different temperature. It handles ballistic, quasi-ballistic, and diffusive transport. And for those of you that are interested in kind of trying this out, there's an exercise that comes with this lecture where you go ahead and you use this tool to essentially replicate many of the figures that I've shown in this lecture. And so I hope that I've given you a sense of how these calculations are done and why, in fact, it's useful to know how to do them. So thank you very much.